Yep. Yes. All right. Let's get started. Who's? I think so. Who's ready for the last day of Tazi?
So we've added week 5.
Okay, so for my last lecture, I will talk exclusively about 4 types of experiments at the precision frontier. I had to make some choices, so we'll finish up with forces mediated by scalars, which can be detected effectively with mechanical resonators. We'll talk about axion-like particles, targeting the QCD axion in particular, using spin resonators and electromagnetic resonators. And then I'll say some words about electric dipole moments in the end, which you can think of as spin interferometers. So I said last time that every precision frontier experiment can be boiled down to essentially oscillator or a 2-level system with states 0 and 1. So this could be spin down and spin up, or 2 levels in some atomic system. And then you can think of the different measurements either as a 2-level resonator, where you start from one state and you're resonantly driven to an excited state. Resonant meaning your driving frequency matches the frequency difference or the energy difference between the 2 states. And the second case is an interferometer, where you look for small phase shifts due to, let's say, small energy between these 2 states. That will be the case for a spin interferometer and is also the case for an atomic clock, essentially. But before I go through those particular experiments, I want to give you just a very brief review of what the fundamental noise sources are in these experiments. So we saw last time that if for example, in this interferometer, if you have some small phase shift, you can read this out by either by having a slightly higher probability of excitation of this excited state versus the ground state. And when you want to read that out, you project on this state or that state, but you'll get a probabilistic outcome. So there is some fundamental quantum projection noise due to the fact that, if you have some 50-50 excitation and you want to ask if you're excited or not, you will get some binomial distribution noise. So that means that your sensitivity to reading out any phase shift phi in this 2-level system will be order unity if you only have one atom, but for many atoms, this will be, or for n independent coin flips, your noise will be suppressed by 1 over root n. If you have entanglement or squeezing, you can, in some case for correlated systems, bring this down to 1 over n, and that's focus of many experimental efforts right now. So that's sort of the fundamental noise source of any interferometer, including EDM measurements, atomic clocks, and in some sense LIGO as well. For these types of systems, so for resonators, a fundamental noise source is often thermal noise or also the standard quantum limit. And for that, I want to just briefly review the fluctuation dissipation theorem. I'll start here, actually. So the fluctuation dissipation theorem is basically a formula that relates small fluctuations in thermal equilibrium to linear out of equilibrium response. And I'll say a few words about that. So basically, if you know, if you poke your system, so if you poke your harmonic oscillator or two-level resonators out of equilibrium very weakly, and you can model well how it responds, right? So if I push a mass on a spring, it will be displaced a little bit, and I can measure the spring constant, the mass of the object on the spring, as well as dissipation or damping of that system. And so once I can quantify that linear out of equilibrium response, then I know the thermal and quantum noise sources in thermal equilibrium of my system. And thus I can characterize the fundamental noise that this harmonic oscillator has as a function of frequency. So I will go over that right now. So I will do it for an electrical resonator first. So some system with some resistance, a capacitor C. I hope you remember this from your electromagnetism lectures, okay? And so we're going to imagine that we're weakly driving this with some voltage, which will be the sum of some signal voltage and some noise voltage. Okay, so it's helpful to Fourier transform. So typically we take our measurements over some time tau. So we take this finite time Fourier transform of our voltage. So this will be, I'm going to start with an electromagnetic resonator, but the same thing will hold for a mechanical harmonic oscillator, for example. And so what we'll be interested in is this power spectral density of the voltage for both the signal and the noise as a function of angular frequency, which I'll write as the integration time tau times the Fourier amplitude squared. Okay, and so then your signal to noise ratio in the end will be power density over your noise voltage. Okay, and so yeah. So if you look at this formula, for example, if a monochromatic voltage, so if it's just a pure harmonic function, then this this will just be this v tilde of omega will just be the amplitude of your harmonic, and your signal voltage will scale like tau times this amplitude squared. But as we've seen, for dark matter signals, for example, it's not a harmonic function. There's some small spread in energy of your signal, and so it's not a purely harmonic function. And at some point, if you integrate for long enough, longer than the coherence time of your dark matter driving force, you'll start to resolve the finite frequency with here. Okay, so the smallest voltage you can detect, so the typical standard deviation on your voltage, assuming signal to noise ratio of 1 here, would be, in such a case, the square root of your noise spectral density times the bandwidth of your signal to the 1/4 power divided by integration time to the 1/4 power. Okay, this is I will put that as an exercise in the notes. And so just to remind you, the typical bandwidth, so the frequency width of a signal for dark matter would be the spread in kinetic energy, so m sigma v squared, where sigma v is 10 to the minus 3 c. It's the velocity dispersion of dark matter in our galaxy over 2 pi. Okay, so if you say I have some dark matter signal that's giving me some quasi-harmonic voltage signal V with some bandwidth delta omega given by this formula, and I integrate for some time tau, then this formula will tell me what's the smallest voltage I can detect. Now we just need to characterize what this noise spectral density is for our noise, right? And for that, we'll use this fluctuation dissipation theorem. I won't have time to go through the full derivation here, but I'll just tell you what the formula is. So what you need is the Hamiltonian of your system without the poking, okay? And so then you will need 2 conjugate variables, so some voltage, and in the case of this system, it would be voltage and effective charge. And so what you need out of your H naught here is the linear response, which is characterized by this complex impedance, right? So it would be, if you drive the system with a purely harmonic voltage V, you can characterize how much charge is being driven through your system, or how much current is driven through your system. And this in general will be a complex quantity, which you can quantify as a real part, some generalized resistance, and some reactance X, which in the case of this RLC circuit would be the capacitance and the. Okay, and so if you can quantify how your system responds to some driving force, then the fluctuation dissipation theorem tells you that the power spectrum of the current, right? So Q dot is some noise energy that I'll tell you in a second, times the complex part of the real part of this impedance, this effective resistance, over the magnitude of this impedance squared. Okay, so I'll have a derivation formula in the notes. And if you want to translate this to some effective voltage noise in your system, this will be the same noise energy as a function of frequency and temperature of your system times the resistance, this generalized resistance. This noise energy is basically at extremely low temperatures. It's just as limited by quantum mechanics. It's the 0-point motion of your oscillator. So it's frequency over 2. And at high temperatures, so at temperatures above the frequency that you're looking at, it's just the temperature. Okay, so that's a very powerful way. So as long as you know how your system responds to some external driving force, and you assume that your system is then in equilibrium, you can figure out what the fundamental noise sources of your experiment. In addition, normally, yes, right? So this is just, yeah, so the question was, do you have to account for shot noise in your experiment? So yes. So this is just the, so this is just a fundamental noise in your antenna, right? So your antenna is some harmonic oscillator, and in general, that the damping in your system, right, basically means that you have some connection to the environment, some noise source, right? So that's where the damping goes. Energy goes out of your antenna where else, right? Something that's presumably in thermal equilibrium. And so if you have less damping or less dissipation, that means you're more decoupled from the thermal bath, and therefore you have smaller fluctuations. So you want some very low dissipation systems in general, right? So you want something with a very low real part of your impedance. On top of that, then, are environmental noise sources, readout noise, amplifier noise. I won't go through them in detail, but I will have some statements about readout noise and amplifier noise in the notes. That's a good question. Okay, I'll leave that here. So let's go to experiments now. So we'll finish up with scalars from last time. So I told you about clocks and how they can look for scalar dark matter. But even if these scalars are not part of the dark matter, we can still look for the forces and potentials they mediate. So if you have two masses A and B, they have a gravitational force from single graviton exchange, but they can also have a force from some CP even exchange. And these diagrams will give you this standard Newton potential proportional to the masses of your, let's say, atoms A and B, neutral atoms A and B over R, but plus some correction that's usually quantified in terms of these alphas with e to the minus mr, where m is the mass of the scalar. So you can think of this as some off-shell production of these scalars. And then by atom A and then particle B feels the gradient of the scalar, which would be some correction to the force. Those alpha A's here and alpha B's would be the fractional change of the mass of the atom with in unit as you vary fractionally this phi over m Planck, roughly. Okay, and so in general, these alphas will depend on the chemical composition of your two bodies A and B. And so for neutral matter, roughly these alpha A's will be will depend on some effective charges and these couplings dG, dMe, etc. So to leading order, you mostly care about the average of these light quark couplings. And this is the coupling to the gluon. And then there's some effective charge from the scalar to electrons as well, and from the scalar to photons. And so for most atoms, for basically any nucleus, most of the mass of an atom will be residing in the nucleus, and it's mostly coming from gluon self-energy. So this charge is effectively 1. This charge is about 0.1. So if you change the quark masses by epsilon, you would change the mass of a typical atom by about 10% times epsilon. But of course, with some dependence on what nucleus you're looking at, this charge is given by the electron to nucleon mass ratio and how many electrons you have, which is assumed to be the same thing as the same number as protons over the overall number of nucleons you have. And then QE here is the most strongly composition-dependent piece. So roughly speaking, this is -1 plus 8 z over a. This term is coming from how much the proton mass changes as you change the fine structure constant. And then there's some mutual repulsion between the protons in the nucleus that scales like this. So this is some empirical formula from nuclear binding energies. Okay, so the fact that these forces depend on the chemical composition of the two gravitating bodies means that the weak equivalence principle is violated, right? So what you can do is you can look for the differential acceleration of two bodies A and B in the potential of a third one, like that of the Earth. So this would be the acceleration of A minus the acceleration of B divided by the average. And so this would be approximately, since gravitational force is not, for gravity, these would be the same. But in this case, this would be proportional to this difference of alphas. So you need the composition dependence. And then, let's say this effective alpha averaged over the Earth or the Sun, whatever the third body is. Okay, so we've done many such experiments of how different materials fall in the gravitational potential of the Earth and the Sun, both in space and with torsion balances on the ground. And we've constrained these differential accelerations, these fractional differential accelerations, to about 1 part in 10 to the 15, with both torsion balances and space-based experiments. So roughly the bounds from on all of these are about 10 to the minus 3 for the coupling to electrons, so 1,000 times weaker than gravity. For the coupling to photons, and for the coupling to quarks and the coupling to gluons, roughly 10 to minus 5. Any questions about this? And so this is assuming, these bounds are assuming that the mass is less than roughly 10 minus 12 or 10 minus 13 electron volts, so the whole force is coherent over the entire Earth, right? So this would be such that the range of the force is the Compton wavelength of the mediating particle, and it would be larger than the size of the Earth, so you have the full coherent enhancement of all of the particles in the Earth or in the Sun. Any questions about this? Yeah, Vincent?
What happens if the force is vector-mediated?
For vector-mediated forces, yeah, you have something. The question was, what if the force is vector-mediated? So for the two examples of vectors that I showed you in the first lecture, which were kinetically mixed dark photons and B minus L gauge bosons, the first one basically doesn't do anything for neutral matter, right? Because it's a kinetically mixed photon, so dark photons. So if you have neutral bodies A and B, they would not feel a force, right, unless they're charged. So in that case, you're looking for violations of Coulomb's law, but you have to be very careful about shielding calculations. For a B minus L gauge boson, I do not know the exact number off the top of my head, but that is not shielded, and roughly there would be the B minus L charge of the Earth, for example, is non-zero, right? Because there's roughly the charge of, for neutral matter, the charge of the protons and the electrons cancels out. But basically, if you couple to B minus L, you couple to all of the neutrons in a neutral body, right? So there's some positive charge for any sort of neutral matter made out of regular stuff. And so then indeed, you would get roughly a correction here, which would be for B minus L. This would be the, you would get, I think here, GB minus L squared over, actually, you would get plus GB minus L squared over 4 pi r, coupled to the, only for neutrons. So you would get something like this with e to the minus mr as well. And roughly, because we've tested this to these effective couplings to 10 to the minus 5. These couplings have to be weaker than gravity by 5 orders of magnitude. So if I remember correctly, GB minus L, again, for this mass range is less than about 10 to the minus 24. Okay, 5 orders of magnitude below m neutron over m Planck. It might be 10 minus 25, I don't know exactly, but it's around here. But for dark photons, the limits are much, much weaker. Good question. Okay, so the second thing we can do is that the force does not obey the inverse square law. So there's lots of astrophysical tests of effectively, violations of the inverse square law. You can look for a precession of the moon's orbit in Earth's field, or in the field of Earth and the sun, or the precession of other planets, or the fact that the effective G Newton that you would see is different on small and large scales, below and above the Compton wavelength of the particle. And so at very short distances, the best probe is not actually to look for composition dependence, but to look for this violation of the inverse square law. And so we've tried this. So if you assume for a second that these alphas are 1, so if you have some gravitational strength coupling, then we've excluded masses below about 5 millieV, which is basically saying we've tested gravity to order 1 corrections to gravity 38 microns. So actually, let's estimate using the fluctuation dissipation theorem, how well we can measure forces, let's say at the centimeter scale, right? So I'm imagining you have some source A and some target mass B. Let's say this effective radius is about 1 centimeter. And generally, your source mass is effectively a harmonic oscillator. Your probe mass is effectively a harmonic oscillator. So it could be a torsion balance that's being torqued, and then the restoring spring would be the torsional stiffness of a fiber. Sometimes at very short distances, this will be on a little springboard or a cantilever, so effectively there, it's also a harmonic oscillator. In some cases, it's a levitated dielectric sphere or disk. being trapped with a laser field. And so effectively the restoring force would be the laser field. But yeah, so let's treat it as some generalized harmonic oscillator and see how far we get. So then the force between A and B in this case would be G Newton, these alphas, so the correction to the gravitational force. And then the total number, the total mass I have, which will be the density, the mass density of both objects. So you want them to be as dense as possible. And then it scales like, the force scales like 1 over r squared. So you see that overall, it scales like r to the 4th. And just for reference, this is about 10 to the minus 10 newtons if your radius is about and both of these alphas are order 1. Okay, so it's a very small force. So yeah, let's use the fluctuation dissipation theorem. So for a harmonic oscillator, I have just this differential equation. Right, so I know how I drive my system. So in this case, instead of voltage and charge, my conjugate variables for a mechanical or harmonic oscillator are force and displacement. Right, that has units of energy. And also, omega squared will be the spring constant over the total mass. So if I use the fluctuation dissipation theorem, in the same way, right? So I would I can ask what's the uncertainty on the force what's the uncertainty on the force? So I would have to know this power spectral density. But I know this power spectral density from this generalized resistance. So this generalized resistance will be proportional to the inverse of this damping factor here. So if you apply the fluctuation dissipation theorem here, and you assume that the spectral bandwidth is just set by your integration time, this is the mass of B times the frequency, the natural frequency of your oscillator, the temperature of your system over the Q factor and your integration time, tau. Okay, so that's the purely Brownian noise in thermodynamic equilibrium of this simple harmonic oscillator. And if you work out what that is for some fiducial numbers, this is 10 minus 15 Newton. And it scales like at fixed density, the mass goes like r cubed. So this scales like r to the 3/2. These torsion balances are often have kind of a restoring frequency of 1 millihertz. So that sets omega naught, and it scales like the square root of that. It also depends on the mechanical quality factor of your harmonic oscillator. So for a torsion balance, that would be the quality factor of the suspending fiber. And this is assuming also room temperature, so 300 Kelvin, and an integration time 100 seconds. And it scales like 1/2. So it's basically saying we can look for forces that are 10 to the minus 5 times gravity at roughly the centimeter scale, and that's roughly the experimental sensitivity at the present. Yeah.
Are they macroscopic objects?
Yeah. No, they would just be, let's say, 2 tungsten balls.
How do you measure the mass
you don't need to know the mass too precisely. So yeah, I didn't actually tell you how it's done normally, but yeah, I guess the simplest case would be, imagine I had some pattern. Actually, this is not how. Okay, but imagine I literally had some ball here, and I knew the mass to a percent. I need to know it to some ridiculous precision. What I do is I introduce time dependence in my system by hand, right? So I can move this ball A sideways, so away from this ball here, and that will drive my harmonic oscillator. Ideally, you want to do it at the natural resonance frequency of your oscillator to excite it and have a larger amplitude. But yeah, so to know the exact mass extremely precisely. Yeah. And so you will see a response, right? The main response would be the gravitational response, but then you can do it at a different distance, and if there is some if now there's an effective change in g Newton with respect to distance, then you can fit for this generalized form, and this would roughly be the sensitivity. Yeah, but you don't need to know the masses to some insane precision to do a measurement like this. Right. So that was one example of basically a mechanical oscillator here. So let's now go to pseudoscalars. So for pseudoscalars, some of the most exciting experiments being developed now are essentially spin resonators. So it would basically consist of a large vat of, let's say, liquid helium or xenon with a bunch of polarized spins, and you're perturbing Hamiltonian, and so yeah, you can put it in some. And you're perturbing Hamiltonian of your system, as I showed you in the first lecture. This derivative coupling of axions. Okay, so I'm neglecting the second term. And so, yeah, so your effective axion field, let's say, is some harmonic wave with some gradient set by the inverse de Broglie wavelength. Okay, so effectively what this does is cause some NMR type resonance, as I'll show you in a second. So yeah, so what we essentially have, so let's consider the state of just a single spin for a moment. In some B field, some B field along the spin polarization axis, this would have a larger Zeeman energy than this one. So I can model the Hamiltonian as some the effective magnetic moment times B naught, right? And then I'm going to assume now that V is, let's say, in the minus y direction. And so that means that my gradient here will be in the y direction, and my perturbing Hamiltonian some sigma y, and sigma y in sort of in the Hilbert space of z-axis I can write as I 1 0 minus 0 1, and the effective driving force here would be proportional to some Rabi frequency times a cosine e to the I omega. I'm going to write it here, e to the I omega t plus e to the minus I omega t over 2, where this omega is proportional to my axion couplings and this gradient mv and the amplitude of my field. Okay, and so yeah, to give you a sense of numbers, so this is some frequency at which I will make the spins precess and sort of go some frequency for driving my system to the excited state. And this omega is about, for numbers relevant for the QCD axion, is about 10 to the minus 15 radians per second of 10 to the minus 8 EV. Okay, so in fact, the way to quickly see this is A over F for the QCD axion. If you assume that it's all of the dark matter, this is about 4 times 10 to the minus 19. So it's a dimensional number. And yeah, so it's mass independent. For example, if the axion mass were lighter, then the amplitude of the field is larger today to make up the same energy density. But there's an inverse mass and coupling relation of the QCD axion. So this number is fixed if it's all the dark matter to be on the order of 10 minus 19. And this is 10 to minus 3c. This is assumed to be an order 1 number. So it's basically 10 to the minus 22 times this mass. And that gives you 10 minus 15 radians per second. Okay, so the response of the system so if we ask how does the system respond, let's say all of the spins, actually I drew it the wrong way here. Let's say all of the spins are 0 initially, so let's say spin down. The evolution of the system would depend on this time-dependent Hamiltonian. Let's say from time equals 0 to some time t, and you started in the state 0. So to a good approximation, well, the largest amplitude is for the state to remain in 0 because the perturbation here is small. But then I would have some excitation here that looks like effectively some sinc function. Okay, and if you're exactly on resonance, this would just be this whole thing would just be omega t over 2, I believe, times excited state. So essentially, what this is saying is that if you start in the ground state here on the Bloch sphere, you would have some excitation frequency along this direction of omega, and as long as I should say axion mass here, as long as your driving frequency matches the natural frequency of your system, you sort of track it around. The spin wants to precess at omega naught, but if you if you track that standard dependence, or I should say this is omega naught. If you track that phase rotation with your driving field, you get some effective Rabi precession of order, Rabi precession frequency of order omega. Okay, so if you integrate for, let's say, 1 second or so, you would get a 10 to the minus 15 sort of spin precession angle of your system. And so how do you read this out? What you would do, or what has been proposed in an experiment called Casper, but there's similar versions of this experiment, is you would read out, so let's say that your signal is that you have some slight, so the spin started in the down position, but you've slightly tipped them from the down position to some slight transverse polarization. So they're precessing around, and so they would have some component in the transverse direction, which you can then pick up with some pickup loop, some conducting pickup loop. So you would pick up the flux from the magnetic field of these transversely polarized spins, and then you would look, that flux will drive some voltage in the circuit that you can then feed to some magnetometer. So this flux would drive some voltage here, drive some current in the circuit, which you can then inductively couple to a magnetometer like a squid. And to an earlier question, so the fluctuation dissipation theorem that I'll show you in a second will tell you the internal noise of this system, right? It's a system that has a linear response. So I can calculate the intrinsic noise fluctuations of this system. Depth noise, right? So there's this magnetometer here has a finite flux precision, for example. But that readout noise I can mitigate. So for example, I can have a transformer, right? Just like we can, you have transformers that go from 120 volts to 5 volts in household appliances, or 12 volts. We can do the same thing here, and effectively amplify the signal and lower the readout noise. But that comes at another cost, because this squid has some fluctuations in itself, and if I couple it too strongly, so if I amplify too much, this noise will then back react on the system. And so there is actually some optimum amount of amplification done so that I mitigate the back action. So there's typically, in most systems, there's internal antenna noise, readout noise, and then back action of your measurement. And you want to optimize your experiment to minimize this. Okay, let's get a sense of the numbers. So the transverse magnetization, and let's say in the transverse direction. So this would be densities of spins, their magnetic moment, and how much, what the sort of the RMS transverse spin, not T, transverse spin polarization is. And so if I have liquid helium-3, this has some characteristic number density of helium atoms in a liquid, and a nuclear magneton. So if you calculate the characteristic magnetic field of such a system, this is about 10 to the minus 4 Tesla. And then the transverse piece is much smaller, right? So I said after about a second, you would have a 10 to the minus 15 spin polarization. So about 10 to the minus 19 Tesla signal is what you're going for, typically with these numbers here. Yeah, and so if we ask what's from the fluctuation dissipation theorem, what's the minimum what's the sort of standard deviation frequency that I can get. I'm not, in the interest of time, I'm not going to go through that. You would have to calculate how these spins dissipate. So the way to do so is there's dipole-dipole interactions, or if there's a homogeneous magnetic field, they can get out of sync, for example. So all of these things are packaged in some effective dissipation time, T2. So T2, so this is the transverse spin relaxation time. And it quantifies how well your spin resonance is. So that's the time after which your spins lose transverse coherence. And so effectively, from magnetization noise limitations, your effective precision on the Rabi frequency is 1 over the square root of that time. So again, it's sort of proportional to the inverse dissipation in your system. The dissipation in your system, and then 1 over the integration time to the 1/4 power, and then as promised, the effective bandwidth of your system. Okay, and this will give you about 10 to the minus 15 radians per second. If for an integration time of 10 to the 4 seconds, and over a volume of 10 centimeter cubed to the 1/2 power. So roughly at standard densities, if I have a volume of 10 centimeter cubed and I integrate for this time, and this number is for 10 minus 8 electron volts, which is kind of the highest it could possibly be. The challenge with these types of experiments is that one of the challenges is that they're resonant, which is good and bad. The resonance means that I amplify the signal, right? So if I get for free the small denominator here, which means I get to integrate coherently for a long time. On the other hand, that means that any one experiment, if I integrate for 10,000 seconds, so 3 hours, I'm only sensitive to axion masses very close to the frequency, to this natural frequency of my resonator. So I have to scan, and I have to change the magnetic field, the sort of background magnetic field that I apply to tune the natural frequency and then do another run. So these types of experiments are tantalizingly close to the QCD axion signal, but it will take a long time for them to get there. And some additional, what I didn't show you is the squid readout noise, which is about a factor of 10 worse at the moment. So there's significant R&D still to be done to get to the QCD axion signal in a reasonable scale, but we're quite close. Any questions about spin resonators?
Sorry, in general, with these kind of experimental setups, do people worry about the fact that you are often basically like measuring zero? So in other words, that's like the most expected signal is the same as if you like forgot to plug in the device.
Yeah. So the question was, are the experimentalists comfortable with measuring zero? And I guess the follow-up comment was, are you sure your system works? So very frequently, these experiments are still in R&D, so this is not done. But to the second follow-up comment, you can inject blindly, in some cases, a real signal, right? So what you can do is, let's say you're the PI of the spin resonance experiment, and I'm your graduate student. I can by hand have some coils next to it and produce some small field in the x direction, some delta bx, right? And I, as a grad student, will not tell you at what frequency I do so and with what amplitude I do so. And then you and your team will do this analysis, scan over all frequencies, and you better reconstruct this blindly injected signal that I did. And so that's true basically in any of these experiments where you can do so. So then you can definitely know that it works. Yeah, to the first comment, yeah, more likely than not, you will measure zero in your experiment. So you need a very daring experimentalist who's philosophically okay with not measuring any positive signal for a long time. Although the QCD axion, I would argue, is quite motivated since it solves a strong CP problem and is naturally produced in the early universe. So I think that's a very subjective view, but it has in our field, a relatively large possibility of existing, giving you a signal.
But at least you can make sure that your thing isn't turned off.
Yeah, you can make sure. And that's true in the next example that I will talk about too. And there it's actually quite common to do so. So in fact, the most successful way to look for the QCD axion so far that has excluded some small mass range around a few micrometers are electromagnetic resonators. So these would be cavity experiments, cavities, or basically RLC resonators. So in fact, the setup, I will draw a very simplified and wrong picture of the experiment. But essentially what is done is you have some cavity or RLC circuit. You could argue a cavity is effectively an RLC circuit with many modes. Is you embed your experimental apparatus in some large magnetic field. So let's say some solenoid. This cylinder is a solenoid, for example. So there's some large vertically oriented magnetic field. And your apparatus has some size L. And the axion signal would manifest as some perturbation to this static magnetic field. So in the first lecture, I derived these axion electrodynamics equations. So to leading or the main term that's not velocity suppressed. So it's only proportional to a dot of your axion field is this. Okay, so you can think to first approximation. You can think of this this effective source term in your axion Maxwell's equations as some fictitious current density J effective. You have to remember that this is not a real current, right? This is not moving electrons or something like this. But you can treat it for the purposes of calculating the resulting magnetic field as some, as an effective current density. Yeah, so the equations are these. But if you treat this as a perturbation, the leading order of the magnetic field is the static one here. And then this will produce some signal B field. And so, yeah, so it would effectively be like an oscillating current along this direction. And if you remember physics 102, or whatever it's designated in your undergraduate curriculum, this will give you some azimuthally oriented B field wrapping around this current density. So I'm not going to solve the equations in detail, but roughly what this gives you, this gradient will be order 1 over the size of your experiment. So the size of this B phi the size of this B phi will be the naive size of this coefficient, which we saw yesterday is roughly alpha over 2 pi. there's this axion amplitude over F, and then the mass of the field from this derivative here. And then this gradient was 1 over L. If I bring that to the other side, I get this ML factor here, and proportional to the full B field here. Okay. So let's look at some numbers. This is the largest static magnetic fields we can create in our lab are on the order of 10 Tesla. Alpha over 2 pi is about 10 to the minus 3. I told you in this example over here that the size of A over F for the QCD axion is about 10 to the minus 19. So in the end, I get parametrically a signal field of 10 to the minus 21 Tesla, as long as my axion Compton wavelength matches the size of my experiment. So the size of the cavity or the size of the inductor that I have in my RLC circuit. And if the mass is much lower, then there's some suppression. This factor cannot be large because if it is so, then my approximation is treating it as some lumped element circuit becomes invalid. In fact, that would lead to some suppression. Okay, so that's an insanely small signal. So it requires a lot of efforts on magnetic shielding, et cetera. But we can ask the same question again. So what's, from the fluctuation dissipation theorem, what's the minimum magnetic field that I can detect? And again, just very simplistically, we can try to detect this magnetic field using the same system. So we can have some effective pickup loop, and then measure it with some squid system. Yes. Question.
So you mentioned the axial wavelength doesn't match the size of the cavity, you have some suppression. Is it like a typical exponential suppression, or you have something that's
In the case of a cavity.
Could you repeat the question?
Yes. So the question was, what happens if your axion Compton wavelength doesn't match the size of your experiment? Then in that case, you do have to distinguish cavity and RLC experiments. So for a cavity experiment, I believe your signal will be polynomially suppressed. Very similar to here, right? So if you're off resonance, instead of being able to integrate all the way to the effective coherence time of your system, which for the spin resonance system was T2, for the cavity system, it'll be some other damping rate, right? So you're some quality factor, there's effective damping rate for that to happen. And so if you're exactly on resonance, your power absorbed is limited by that quality factor. But if you're off resonance, you're limited by the inverse detuning of frequency. So it's in terms of power, it'll typically be quadratically suppressed. But these cavity resonances are very narrow. So even a quadration is quite bad away from resonance frequency for cavity experiments. For RLC experiments, again, they're also resonant harmonic oscillators. So there's this similar polynomial suppression. But in that case, if you can tune your inductance very large and your natural frequency can be much lower than the inverse size of your system, and so you can go to lower frequencies. But then you do just pay this linear suppression. Yeah, but then the formula is invalid if this is larger than 1. Yeah, but yeah, it's typically polynomial suppression that's quite severe. So you want to work on resonance where you have maximum energy transfer from your axion field into your system. that's usually the figure of merit. Maximum energy transfer from your dark matter field or your new physics into your harmonic oscillator, because that also helps with readout as well, right? If you have a lot of energy transferred, then it's easier to read out the system and avoid back action. Other questions? Yeah.
How scannable is this one, given that it's based on the size of the experiment?
Yeah, that's the most sensitive experiment. Yes, the question was how do you scan the system? How do you scan the natural frequency of the system? So the most sensitive experiment is a cavity type experiment called ADMX, and there's other ones. What they do is they have tuning rods, so they will so your harmonic oscillator in that system is some electromagnetic mode inside your cavity, and some conducting rod or conducting rods inside the cavity. You functions of your cavity modes as well as the eigenvalues, which are the natural frequencies. So you can and you can also look at higher modes, like a cavity doesn't have one mode, right? It has many modes. But generally, you can scan to within 1 octave, like a factor of 2. So omega naught will be of order 1 over your cavity size times some number that's order 1, and you can sort of tune within that range. But if you want to go a factor of, this cannot be 10. Yeah, so for that you need to build a smaller cavity. And in fact, that's why high-frequency axion searches are quite difficult, because either you need to build smaller cavities, but for smaller cavities, you have less energy in your system. So these numbers would more or less be the same, but you have less energy in your system, and that means reading it out is harder. So you would need to multiplex many small cavities and add them up coherently. For RLC circuits, it's fairly easy. You just change the inductance of your RLC circuit by increasing some extra windings in your solenoid, for example. So in that case, scanning is easier. So these RLC circuits, they go by the name of an abracadabra, which I've now merged, I believe. Dark matter radio. Any other questions? I have 7 minutes. Okay. I think that's more or less on time. I didn't say what the minimum sensitivity was. Okay, so again, from the fluctuation dissipation theorem, in this case, right. Since I only have 7 minutes, I will not go through the derivation. I'll just tell you the answer. So it's, again, proportional to the temperature of the system, and then the quality factor of your cavity or your circuit, and the frequency squared. And I'm assuming everything is optimally matched, like this factor is 1, etc. And then again, this is the bandwidth of your axion signal to the 1/4 power, and your integration time to the -4/2 power. And so if you plug in the low temperatures at which these cavities work, hundreds of millikelvin, if I remember correctly, and their quality factors of about 1 million, you get 10 to the minus 21 Tesla. This is 10 to the minus 21 Tesla per square root of Hertz. And so for typical coherence times and integration times, you would be able to get down to 10 to the minus 21 Tesla, which is the size of your signal. So these experiments, in particular, ADMX reached unit signal-to-noise ratio for axion-photon couplings as expected from the QCD axion. So in the last 5 minutes, I just wanted to tell you quickly about electric dipole moment experiments. So they're, I think, at the precision frontier at least, the most sensitive probes of very high energy physics indirectly. Again, so we saw last time, right? EDMs will give you some Hamiltonian. That's the spin dotted into the E field. Okay, and so effectively what you do in an electric dipole moment experiment is you have your spin system. Let's say this is spin down and spin up of the neutron, for example. You start with your system in the spin down state, and then you apply some magnetic field, and your spin is pointing in the, I guess, minus x direction in this case. So effectively, that means it's in a superposition of spin up and spin down. And if then you apply some electric field in the z direction, the largest magnetic field we can apply in the lab before you get electric breakdown is about 10 kilovolts per centimeter. So that means that spin up and spin down in zero magnetic field, but this electric field would have some different energies. So that means that this spin would precess very slowly in this equatorial plane. So to go from here to here, I applied some pi over 2 pulse with some E field pointed along this axis. If I did that again, right? So I let the system evolve for some time tau, right? So I let it evolve freely in this electric field for some time tau, and then I apply some other pi over 2 pulse, meaning I turn on a brief pulse of a magnetic field again along this axis. And if there was no electric dipole moment and my spin had kept pointing in the minus x direction, then now it would be pointed in the z direction, and I would have flipped the spin because I did some pi rotation from spin down to spin up. But if my spin had precessed, for example, all the way over here because of this interaction, then a pi over 2 pulse is not going to bring me to the excited state, but to the ground state. So effectively, I can measure, as I said here, any phase shifts from precession to order 1 over root n if I do this experiment n times. So my uncertainty on this precession frequency omega is roughly 1 over this free precession time over root n, the number of times I do this experiment. So I get a precision of order 1 over the maximum size of the E field over square root of n. Okay, so from here, from doing this with ultra cold neutrons, the electric dipole moment of the neutron is constrained to be 10 to the minus 26 E centimeters. So the way to quickly derive the sensitivity is if the electric dipole moment was this small, in a 10 kilovolt per centimeter electric field, that would have given me, so that would be 10 to the 4 volts per centimeter. So that would be 10 to the minus 22 EV precession frequency, which is roughly 10 to the minus 7 radians per second. So that's sort of the angular frequency of the precession in the largest electric field we can create. And so the free precession time of these neutrons is about 100 seconds, so that would be 10 to the minus 2. But then they've done this for roughly a billion or several billion neutrons over multiple years. So that gives you another 10 to the 5, and means they were able to achieve this 10 to minus 26 e centimeter sensitivity. So I'm over time. So I will just, I will have in the notes how, for example, these experiments may improve with, for nuclear EDMs and for electric EDMs. In fact, the best limit on the electron EDM, so this is not the scalar phi coupling, this is the electron EDM, sorry for the abusive notation, is about 4 times 10 to the minus 30. From an experiment done by Eric Cornell and Journier here on hafnium fluoride plus in some ion trap with a very similar principle, except the electric